Okay, so this is 17.6, surface integrals. So we're finally going to be able to integrate on surfaces, such as the surface of a sphere or the surface of a paraboloid. And luckily for us, the concepts are very analogous to the same concepts we saw with parametrization. Some of the integration stuff we'll be doing is just a direct extension of what we did with integration into plane and in particular change of coordinates. All right, so what we want to do is, the picture of what we want to do is we have a surface of some kind. So by surface, we mean a two-dimensional object. And again, by two-dimensional, we mean if you're standing on the surface of that object, if you're standing, let's say, on the object, how many different directions are you able to move, right? So if I'm standing on this object right here, there's essentially two directions I can move. I can move that way and I can move that way, right? I have the opposite directions, but that's just negative of the first direction. And I have this opposite direction, which is negative of the second direction. So that's in a way the same, right? And then everything in between is a combination of these two guys, right? So essentially I have two directions I can move. So just think about like on the, in practice, right? You are able to move in two directions being on the surface of the earth, right? You can move east and west, and you can move north and south, right? You can't really move up and down so much. So that means, as far as you're concerned, the earth is a two-dimensional object, all right? Okay, on the other hand, let's say to an airplane, the earth is a three-dimensional object because it can move east, west, it can move north, south, and it can move up and down in elevation, all right? A one-dimensional object would be like a curve, right? So if you're an ant on a rope, crawling along a rope, you only have one direction you can move, right? Forwards / backwards. So one-dimensional, okay? So this section, we're integrating on surfaces, so two-dimensional. When we say the word surface, we mean two-dimensional, all right? So we're going to be working with two-dimensional objects. The surface of a sphere, like we said, the surface of a cylinder, the surface of a paraboloid, all right? As opposed to, there's no such thing as like, when I say surface of a cylinder, there's no inside of the cylinder. When I say surface of a sphere, there's no inside of a sphere, okay? It's good to keep these concepts kind of in your mind because we have a lot of different kinds of integration. In the last section, we'll be doing integration, mixed integration, 3-variable and 2-variable surface integration. So it's really easy to get confused as to what kind of integral you're supposed to be working with. So if you're kind of always aware of what dimension your object is, then you know this should be a double integral, this should be a single integral, and so on. Okay, so how are we going to study this? So we want to study surfaces, right? On the face of it, it's kind of hard because surfaces are curved, right? We would like to do stuff, all the same stuff we do in calculus, we want to do on a surface, right? We can have functions on surfaces, just like on the Earth. We can talk about functions on where the input are points on Earth, right? One example is altitude, right? On the Earth, you have a function. The input is your location on the Earth. The output is the altitude at your position, right? Or maybe the input is your position on the Earth, and the output is the temperature, right? So these are functions that are super relevant to our daily lives. So we want to be able to study functions, and in order to study functions, we want to be able to do calculus, which means differentiation, integration in particular. All right. So we're very interested in integration. Okay. All right. So how are we going to do integration on a curved surface? Right. We don't know how to do that now at this moment, because we only know how to work with kind of the plane, right? As a two-dimensional object, in terms of two-dimensional objects. So what we're going to do is what we've always done in math, which is convert problems from difficult problem to one that we already know how to do. All right, so we would like to do integration on this guy right here, on this curved surface. What we're going to do is we're going to transform the problem into a problem on the plane. All right, so what we're going to do is we're going to find a mapping, right, from a portion of the plane. So I'm going to draw it as a rectangle, but it doesn't necessarily have to be a rectangle. It could be a region in the plane with wiggly boundary and all that, right? But ideally, in a way, we would like a rectangle would be convenient for us. Okay, so we want a mapping from the plane to the surface, and again, we call this a mapping because now this is even closer to, we've used the word mapping before, but this is even closer to what we mean colloquially when we talk about the word mapping, right? So this is a position on, let's say, this hill right here, right? And it's represented on our map by that point right there, right? This is a second position on our hill. It's represented on our map right there. Okay, so you can pretty much even just literally think of this as a map, right? And the idea, again, is we're going to do calculus on the map instead of natively on the surface. And again, we'll have the usual complication of calculus on the map doesn't necessarily correspond completely with calculus on the surface. So there has to be these compensation factors when we do, for example, integration. And that's a big part of what we're going to talk about in this section. Okay, so this is a map. All right, our book also uses the word transformation. Unfortunately, our book continues this notation of using vector-valued functions, which again is super silly because we're not really thinking of the output as vectors. We're almost always thinking of the output as points, right? So this point right there on the map corresponds to that point right there in the real world, right? Or on that surface. This point on the map corresponds to that point in the real world. We're not really thinking of this point right there as a vector, right? Or that point right there as a vector. So I hate it very much, but that's how our book has decided to present this section. So I'll try to keep with it a little bit, but I'll often write things in a slightly different way. So let me first do the notation. I guess I shouldn't have put the X and Y here. So generally our setting is going to be like this. We have an object in space, right? A surface in space, sorry. And we have coordinates in space. And generally, at least for our class, we're going to be doing X, Y, Z for for space. And so our surface will be described, in terms of X, Y's, and Z's. Okay, and generally we're going to stick to U's and V's for our map. Okay, so this is kind of good because we used the same notation when we talked about change of coordinates, right? We kind of started with our native coordinate system in terms of X and Y, and if we didn't like how to integrate in terms of X and Y, we converted to U's and V's. All right, so here we're keeping consistent with that kind of idea. All right, we're gonna, like I said, a lot of the stuff we're gonna do right here is an extension of that change of coordinates business. And in fact, if you look at that change of coordinates section, it's in a way, you can think of it as kind of gimmicky because the way they use that section or use that material was to help you change coordinates to integrate, right? But here, we're using the same ideas for a much more important purpose, right? To be able to study surfaces in space. Okay. All right. So we have this map notation. So this is the notation our book uses. So our book calls them R's with an arrow because vector valued function. Again, I really hate that, but we'll try to keep with it a little bit at least. R of UV, right? So the inputs are U's and V's, and the outputs live in the X, Y's, and Z's. All right. So the output should be 3 coordinates or should be 3 things, right? So X of UV, Y of UV, z of uv. And each of these, of course, is individually a function in terms of u and v. All right, again, our book likes to use this, think of this as vector value functions, so the sharp brackets, but it's better to think of it as a mapping. So oftentimes I'll just dispense with this R business, and I'll just write kind of, I'll write a mapping as x of u comma v, y of u comma v, z of u comma v, like that, like equals whatever the formula is. So for example, u squared, just making something up, u v plus u log v times u. Okay. So in the same way that we often wrote curves, right? So technically, vector, if we wanted to talk about curves earlier on in the class, we would have written something like this, right? But it ended up that we often just wrote a curve like this, x of t equals y of t equals, right? Cos t, sine t, something like that. So I'll use this notation more because I hate the vector value notation. It's so unnatural. One of the reasons why it's so unnatural is because it kind of depends on the origin, right? Because when you talk about a vector valued function, your output's a vector, and you're always thinking of the output as the head of the vector. So if this is my output, your vector is that guy right there, right? But what's unnatural is that this point being the origin, why is that point the origin, right? Why is not this point the origin right here, right? So it's very unnatural. It's a very arbitrary choice there. So I really don't like it, with the exception of the situation where you're working with perhaps a rotational motion about the origin, in which case there it's a little more natural, because the origin, if you're rotating about the origin, for example in the plane, then the origin has natural meaning, right? It's the center of your rotation. So it perfectly makes sense to consider the origin as part of your world in a way. Okay, so let's start with an example, a curve example, because we actually want to talk about a kind of a direct analogy or direct extension of that idea. So let's draw a curve. So parabola, y equals x squared. So this is again in x and y. So when we talked about parameterization of curves, we had the t space, right? So this was t. If we wanted to parameterize something like a parabola, we would do something like, so let me use the R notation again, R of t equals x comma x squared, right? This is a nice convenient parameterization, sorry, t comma t squared, nice convenient parameterization for a parabola. So t, right? Where kind of the inputs and outputs are related like this. When you move along here, right, you're in a way just moving along here and then pushing yourself up to the parabola. Okay? All right, in terms of kind of the better, in a way, notation, x of t equals t, y of t equals t squared, right? Again, this is alternate way to write it. Or, sorry, I should put an arrow up there, right? Or sometimes I even like this even better, f of t equals parentheses t comma t squared, right? To emphasize that's a point, and no arrow on top here because it's not a vector. Okay, so this was a standard way for us to create parameterizations out of a function, right? So if we had a different function, let's say this is the graph of y equals f of x, right? Then a parameterization we could use is r of t equals t comma f of t. All right, and that works because, right, t describes your x position, and then where are you? How far up do you have to go to hit the graph? Well, literally f of t, right? That's the meaning of the graph. Okay. All right, that said, let's move on to surfaces. Let's say I want to do a mapping or parameterize, we use the same word parameterize, a paraboloid. All right, so paraboloid here, z equals x squared plus y squared, let's say the most simple paraboloid in a way. How do we do that? Well, we do literally the same idea. So now we need two variables, because again, we're going from a plane, the UV plane, to space. So we need two variables, UV. And we need three outputs, or three functions on the right-hand side, right? The x component function, the y component function, the z component function. And just like we use r of t, t kind of represented the x, right? So here u is going to represent the x, v is going to represent the y, and then if u is x, v is y, what is z? Well, literally we have the instructions right there. Z should be equal to x squared plus y squared, right? So z is equal to x squared plus y squared, x is u, y is v, so this is going to be u squared plus v squared. Okay. So this is, if you look at the upstairs, r of t equals t comma t squared, direct extension of that idea. All right. And again, in kind of the better notation, x of uv equals u, y of uv equals v, z of uv equals u squared plus v squared. Also, I also like this second kind of way of writing it, because we can literally see the x depending on the u's and v's, the y's depending on the u's and v's, and so on. All right. Just that small thing of writing the x equals something, y equals something, z equals something can help us a little bit, because we have, again, we're going to be looking at partial derivatives, and then there's always this question of partial derivatives of what with respect to what. It's easy to get kind of confused, especially when you're first learning this. So here you literally have it spelled out for you that x depends on u and v, y depends on u and v, and so on. All right. So very, very small thing, but I think it can be actually quite helpful. Okay, so with this said, every point here now corresponds to a point on the paraboloid through this mapping, right? So the point, for example, 1 comma 2, that's going to go to x equals 1, y equals 2, z equals 1 squared plus 2 squared, right? Just following the instructions from up there. All right, so 5. Okay, so let's actually label this. If this is 1, that doesn't look, let's put it here. That's 1, that's 2, right? That point goes to, so this is x, y, z, right? 1, comma 2, comma 5. Okay, there's a shadow. Oops. Okay. So the idea is that any problem that you want to solve involving, for example, 1 comma 2 comma 5, you would port that problem backwards to a problem involving 1 comma 2 in terms of u and v. Right, so your XYZ problem becomes a U and V problem, and immediately you can see that this is better, because on the right we're working with X, Y's, and Z's, which is 3 things, right? But on the left we're only working with 2 things, U and V. So immediately you can see that things are going to be a little easier. Okay, now sometimes we're not interested in an entire paraboloid, right? So what happens if we're interested in z equals x squared plus y squared, but only the parts of that below the height of 16, right? So below the height of 16 means z less than or equal to 16, all right? Okay, so the paraboloid is this guy here. And again, this guy here is 2-dimensional, because if we have a 3-variable situation, x, y's, and z's, and you have one equation, z equals x squared plus y squared, then generically that's going to be a 2-dimensional object. All right, so you know that this guy, even if you don't know it's a paraboloid, you know in general it's a 2-dimensional object. All right, so this guy here, z less than or equal to 16, this is not a surface, by the way, because when z is less than or equal to 16, it's a chunk of space, right? Everything in space where the z coordinate is less than 16 or equal to 16. So this is actually a three-dimensional object, all right? What we're working with right now is the part of the two-dimensional object that lies within this three-dimensional object. All right, so be very careful about that. It's easy to get, when you see both of these expressions, right, it's easy to get confused. What is the object you're trying to work with, right? So here we're trying to work with the paraboloid, and this thing over here just gives me a description of which parts of the paraboloid I'm specifically interested in. Okay, so of course the picture is something like this. And here's 16. We don't care about anything that happens up here, all right? So if we want to do this, of course, we need to know if we want to port our problems back to kind of UV. And again, we're still using this x of UV equals, u, y of UV equals v, and z of UV equals u squared plus v squared, right? Because this still describes the paraboloid, right? So what does z less than or equal to 16 tells me is going to tell me is which portion of the UV plane I'm interested in, all right? So my parameterization is still the same, but I'm now interested in which I now need to figure out which portion of the UV plane, right, I care about. Because some portions of the UV plane are going to represent points that are not on the part of the paraboloid I'm interested in, right? So for example, this point right there, if it represents that guy up there, I don't care about it, right? So I want to know which parts of the UV plane I care about. And again, this is, every problem is going to be a little different depending on how your problem is being described, right? But here we can see, well, if I want z equals x squared plus y squared and z less than or equal to 16, that means I need x squared plus y squared less than or equal to 16, right? Why do I want to write it like that? Well, this is useful because I know that x and y relate very easily to u and v, right? Because x is just u and y is just v. So for this particular problem, I want to relate things into x and y, right? And immediately you can see, right? This means u squared plus y squared less than or equal to 16. Okay, so the z less than or equal to 16 directly corresponds to u squared plus u squared plus v squared less than or equal to 16. Okay, and what does that mean? That means that we're interested only in a circle of radius 4 in the UV plane. All right, so for this particular problem, we don't care about things happening outside the circle. We only care about things happening inside the circle. All right, so when we integrate, let's say we want to integrate on this portion of the paraboloid, right, z less than or equal to 16, then that means we're going to be integrating instead in a UV plane over this circle. All right. Okay, alternatively, just a small modification. If we just said we want z equals x squared plus y squared, and we want the part below z equals 16, right? Then what you could say is, okay, I know the pictures of this. I know the intersection of these two guys determines the boundary. And then where's the intersection? It's where x squared plus y squared equals 16. So that means the boundary is u squared plus v squared equals 16. And so that's how we get this boundary right here. Okay, so that's just the alternate way to reason this out. All right, maybe this is too simple. So let's do another kind of version of this. So describe paraboloid z equals x squared plus y squared, but only the part below 3x plus 4y plus z equals 0. All right. So again, we care about the paraboloid in space, but we don't care about all of it. We only want to study the part that's below this guy right here, which is a plane, right? Something x, something y, something z equals a number, right? But now this is not as simple as above because this plane is tilted in some way. So maybe it looks something like that. And so the intersection is going to be something a little more complicated than just a simple circle as above. Okay, but the idea is still the same, right? How would you do this? Well, what does it mean to be below this plane? It means that the z coordinate has to be less than or equal to. Actually, I don't want 0. I want, sorry. Let me make it 12 or something like that. It doesn't matter. Oh, okay, too late. I left it as, I'm gonna leave it as 12. Yeah, it didn't really matter, but I guess we'll leave it like this. So that means z is less than or equal to, that means z is less than or equal to 12 minus 3x minus 4y, right? That's what the word below tells me, right? Below has to do with z, right? I want the parts below the plane, right? If the plane is z equals 12 minus 3x minus 4y, then the part below the plane is where z is less than that, okay? So this is the part that's below the plane, right? And again, we want z to be less than this, but we know z is equal to x squared plus y squared because we know we're on the paraboloid. We only care about points on the paraboloid. And so that means we're interested in this, right? And again, we like this because the way our parameterization is set up, x of uv equals u, y of uv equals v, z of uv equals u squared plus v squared. The way we've set up our parameterization, x and y's relate easily to the u's. So instantaneously, I know that I only care about points where u squared plus v squared is less than or equal to 12 minus 3u minus 4v. All right? And so whatever this guy describes, this is the region of interest in the uv plane, right? So if I want to integrate over the paraboloid below this plane, which we're going to want to do in the future, near future, we're going to want to integrate actually in the UV plane over this region right there, whatever it is, right? And what is it? Well, we can just throw everything to the other side. U squared plus 3u plus v squared plus 4v less than or equal to 12. We can complete the square here, complete the square here, right? We're going to get a circle, right? So u squared plus 2 times 3 over 2u, this tells me that I need to add 3 over 2 squared, so 9 over 4 minus 9 over 4 plus v squared plus 4v plus 4 minus 4 less than or equal to 12, right? Oops, right? These three go together, these three go together, which tells me u plus 3 over 2 whole thing squared plus v plus 2 whole thing squared is less than or equal to 16 plus 9 over 4, which is equal to 73. All right. So ultimately, this thing is, so the region we're interested in is a circle. Oops, that's a 2 right there. With center here, oops, sorry, minus center here, right? And radius like that. So while it's a circle, it's certainly not as simple as a circle about the origin, all right? So things are not always super simple. It completely depends on what you're actually interested in, what region you're actually interested in. All right. And again, once we start integrating, we're going to be converting the problem to this circle here. But if you don't really like this circle, you can always do a change of coordinates, right? And then modify this circle to do a further simplification of your problem. All right. So always keep that in mind. All right. So in essence, we basically know how to work with graphs, right? Or how to parameterize a graph. Like we said, you can always write it as, the kind of most straightforward parameterization would be x of uv equals u, y of uv equals v, and z of uv equals whatever your function is, f of uv, right? So this is if you're talking about a graph where f of x comma y, right? Obviously, if you have a graph that's based upon, let's say, the x and z, right, where the output is y, then you could just switch these variables around, right? In that case, x would be u maybe, z would be v, and y would be f of uv, right? So that way you can do kind of sideways graphs, all right? Okay, just like, so that would be analogous to doing a parameterization of x equals y squared, right? Where you do, instead of writing it as y equals square root x, in which case you're going to have this plus or minus issue, you just do the parameterization t squared comma t. All right, so same idea, you could do that there. Okay, however, the problem is that not everything in the world is a graph, right? One of the things that we really would like to work on in practice, right, in real life, is the sphere, right? Because, you know, it represents the Earth, perhaps, right? So that's obviously of interest to us. The problem is the Earth cannot be, the surface of a sphere, the sphere, cannot be thought of as a graph of a function, right? Just like the circle cannot be thought of as a graph of a one variable function. If you did want to work with the graphs, you'd have to break it into two graphs, the upper hemisphere, upper semicircle, for example, and then the lower semicircle. So with the sphere, you could break it up into upper and lower semicircles, but then you'd have two problems instead of one. So what do we do in these situations? Well, specifically for the sphere, we already have a nice parameterization, right? So let's say we want to work with the sphere of radius 10, all right? So we already have this parameterization in a way because we know spherical coordinates, right? So any point on this sphere can be described in terms of rho, in terms of phi, and in terms of theta, okay? And luckily for us, we're interested in the sphere of radius 10, exactly. So all our points on our sphere, of course, have distance 10 from the origin. So we are only interested in rho equals 10, right? So rho is just a constant, right? And so now we can see if you want to describe a point on a sphere, just use phi and use theta, right? And we've said this before, that makes sense in terms of everyday life because phi and theta are just latitude and longitude, right? Phi is your latitude, right? Because it describes, so here's your z-axis. It describes where you are here, right? That's your phi. So here's your phi, right? Your phi describes where you are. Latitudinally, I guess. And theta describes where you are as you circle around the globe, east to west, right? And so that's longitude, okay? And so our parameterization is just going to be, need phi and the theta, right? And this is something that makes sense because we're talking about a two-dimensional surface. And so we expect two variables to describe it, right? If you're describing a two-dimensional surface using, if you're trying to parameterize a two-dimensional surface and you're using three variables, you've done something wrong, all right? If you're trying to parameterize a two-dimensional surface and you're using one variable, you're doing something wrong, okay? So now everything makes sense. We've got two variables describing points on the sphere, right? Latitude and longitude. And so we've essentially just got our parameterization. And instead of using, we'll try to keep with u and v's as much as possible just because we're kind of so used to it, especially from the change of coordinates section. But here it's just so natural to use phi and theta that I'm going to use phi and theta, right, instead of u and v. If in a way you're uncomfortable with that, just substitute, let's say u equals phi and v equals theta for all my phi's and thetas. All right. Okay. But so my parameterization is going to be this: x of phi theta equals something, y of phi theta equals something, and z of phi theta equals something. All right. Again, in terms of my U's and V's, in place of my U's and V's. All right. So what are these going to be? Well, we already know because from the spherical coordinates section we learned the conversion from spherical coordinates to XYZ coordinates, right? So the conversion was rho for x. It was rho cos theta sine phi. But again, here we're talking about distance equals 10 from the origin always. So the rho is always 10. All right, and the rest of it just stays the same. Rho cos phi sine, cos theta sine phi, right? Y is 10 sine theta sine phi, right? And z was rho cosine phi, so 10 cos phi. Okay, so this is going to be my parameterization. All right. Okay, and again, if you're kind of uncomfortable with it in terms of the formulas and stuff, and if you think you might get confused between the XYZs and the phis and thetas and stuff, just convert everything to U's and V's, right? So this is 10 cos U sine V. Whatever you're comfortable with is fine. Of course, the ideal situation is just to be comfortable, in all situations. But if you're first, when you're first learning these, it's sometimes hard to get used to having lots of different kinds of perspectives. Okay, but obviously these are the same things. These two are the same description of the sphere. And again, this is really nice because literally what we're doing is we're describing latitude and longitude. Sorry, I paused it by accident. All right, so which portion of the sphere are we, which portion of the phi theta plane are we interested in, right? Which phis and thetas are we interested in when we're working with this sphere? Well, if I draw an axis, let's say phi and theta, like this, right? And it doesn't matter which one is x and which one is y. But I've kind of arbitrarily chosen phi comma theta, all right? So which phis are we interested in? Well, phi, normally when we do spherical coordinates, right, we're interested in phi from 0, which is the vertical angle, to phi equals pi, right? So 0 to pi. Okay, and theta goes all the way around. Obviously, we don't want to go around twice because then we'd be covering the sphere twice, right? And so we go 0 to 2 pi. Okay, so we're actually interested in this region right there. Okay, so this region describes the sphere, right? Where one point in the region mostly describes one point on the sphere. Okay, what I mean by mostly is, of course, in spherical coordinates, there's this major issue that when theta is equal to 0, that's the same as theta equals to 2 pi. So this point down here is actually describing the same point as that one up there. All right. So that usually is a bad thing when we do these kind of mappings, because we want one-to-one mappings where one point corresponds to one point, right? We've talked about this before in terms of substitution and stuff like that. But luckily for us, our application here is mostly integration and integration over the region, over this entire region. And when you're integrating over a region, in essence, what's happening along lines don't matter because they're too small. All right. And so even though there's duplicate of this line up there, it's not going to functionally matter for us. All right. But it is something that you should be at least a little bit concerned about when you do see that, when you do realize that this is the case. All right. Okay. By the way, of course, in the same way, there's an issue with phi equals 0. Because phi equals 0 and theta equals anything, these guys all represent the same point, right? And finally, these guys here all represent the same point as well. All right, but again, because they're kind of only curves in space, and because we're interested in integration, it's actually functionally for us not going to matter. Okay. By the way, we've been using the word mapping. Now this is literally mapping, right? When you look at a paper map of the Earth or a map of the Earth, a flat map of the Earth, right, on your smartphone, right? It's literally this thing right here, right? These lines here go to these lines here. I guess maybe it's a map turned sideways, right? Or at least how we usually look at a map. It's turned sideways. Those guys here go to these guys here. So it's literally a map. So here you have the United States, right? And so here you would have the United States. So same thing, okay? So we're actually very, very used to this concept of mapping in a way, just from our everyday lives. Okay, so this is a really nice example because it shows us that this parameterization idea is very broad. It doesn't have to be restricted to just graphs. All right. Okay. What about this? So we just talked about spherical coordinates. Well, we also had the concept of cylindrical coordinates. And for cylindrical coordinates, things that were easy to describe, or one of the types of things that were easy to describe, were vertical cylinders, right? So let's say we have a vertical cylinder of radius 4, right? So this would be x squared plus y squared equals 4. How could you parameterize this, right? And again, you can't do this with a graph. Well, certainly not with a graph in terms of x and y, where the output is z, because there's an infinite number of points above every z point, right? You could think of this as a graph of, let's say, where y is the output and x and z are the inputs, but then you'd have to split it up into two cases, right? One half of the cylinder is one function, the other half of the cylinder is a second function. So again, not that straightforward in a way. However, because we know there's such thing as cylindrical coordinates, we know we can essentially use cylindrical coordinates to describe this, right? And how would we do that? Well, you just think about this. What are cylindrical coordinates? Cylindrical coordinates are where you use r theta and z, right? But here, the nice thing is that we're talking about a cylinder of radius 4, and so r is just 4, right? R is always 4 for any point on this cylinder, right? So r is equal to 4. And so that leaves z and theta and z, right? So that means theta and z describe points on a cylinder, right? And in fact, of course they do. Theta describes where you are kind of rotationally, right? And then z describes how high you are, okay? Which point, how high your position is, okay? So if we look at a phi theta grid, the theta grid where theta is moving and z is fixed would be like these, right? And where z is moving but theta is fixed would be like these. All right, so essentially what we're going to be doing is we're going to be gridding up the cylinder, right? Breaking the cylinder into a grid using thetas and z's. And so of course, here's theta z, literally let's do that. Theta from 0 to 2 pi, right? Because we don't want to go around multiple times and repeat ourselves. So we only care about parts between 0, theta equals 0 and theta equals 2 pi. And of course z, if we're interested in the entire cylinder, z is unbounded, all right? So z can be anything. So we're interested in this region, okay? And again, a grid like this, right? These vertical lines would go to the vertical lines here on the actual cylinder. And these horizontal lines in the theta z plane would go to circles in the xy's on the cylinder, okay? Let me kind of shade those in. So these guys, right, go to these guys here. And these guys go to these guys here. Okay, in terms of the actual formula, right, what we would be doing is x of theta z equals y of theta z equals z of theta z equals. And what is it? Well, we already know the conversion from xyz, from theta, r phi theta to xyz, right? It's going to be r cos theta for the x. R is 4, so 4 cos theta, right? R sine theta, so 4 sine theta for the y. And then z is just z. All right. And again, it's okay, right? Because on our map, we are using thetas and we are using z's. Okay. All right. Let's do one more example. And that's going to be a cone. So let's kind of just think about the kind of usual cone, or the most simple cone, z equals square root x squared plus y squared. Okay, the 45-degree cone, right? How do we do this one? Well, we actually have two options, because the cone is easily described in both spherical and in cylindrical coordinates, right? In spherical coordinates, the cone, this cone right here, it's a 45-degree cone in that every point on the cone is an angle of pi over 4 from z, right? And in fact, that literally describes this particular cone. Okay, so so this is just phi equals pi over 4, right? Which means every other point is described by rho and theta, right? Which makes sense, right? Because rho would describe how far up the cone you're at, and theta would describe, you know, rotationally how which exact position on the cone. Okay, so we can actually parameterize this guy using using spherical coordinates, using, you know, rho and theta naturally, right? So our parameterization would be something like rho comma theta, y of rho comma theta, z of rho comma theta, and we just, you know, copy down the formula we have from spherical coordinates, except we know that phi is pi over 4, is always pi over 4, right? So this would be rho cos theta, and then sine phi, right? Sine pi over 4, root 2 over 2, all right? Rho sine theta, sine phi, root 2 over 2, okay? And then rho cosine cosine phi, root 2 over 2. Okay, so this is a quick parameterization of this guy right here. However, on the other hand, we know that we can also describe the cone easily in cylindrical coordinates, right? Because this cone here, if I think about it in terms of cylindrical coordinates, z, let me just draw z and r. This is, like we said, this is 45 degrees here, right? And so this line right here is z equals r. Okay, and so z equals r literally describes this cone, right? Every point on the cone satisfies z equals r. And so we can use cylindrical coordinates. Let me draw a picture like, sorry, let me draw the picture down here. So we can use cylindrical coordinates where, so cylindrical coordinates are r, phi, and, r theta and z, right? Where the r describes kind of how far out we go this way, right? And you just go up to figure out where you are, like that, right? And then the theta describes how far, again, your rotation. Okay, so x of, so r is equal to z, so that means we can just choose one of them to be kind of our parameterization variable, and the other is just going to be easily converted just by z equals r, right? So for example, if I use, I don't know, it depends on whichever one you find more natural. Let me just use r and theta, all right? Is equal to something, y is equal to r theta, z is equal to r theta here, right? And this is just going to be, what is this? R cos theta, right? R sine theta. Z is equal to what? Well, z is equal to r. Okay. So this is a parameterization. Maybe not this, maybe perhaps not the most natural one in a way, because if you were to describe this cone, I think maybe it's more natural to say how high you are, right? And then where you are around, right? So maybe in a way it's more natural to use z, in which case we can just go z theta, y z theta, z theta, right? And then you would have z cos theta, right? Because r equals z sine theta, and z is just z. But of course, literally, this is just a matter of perspective because these two are literally the same parameterization. I've just renamed a variable. All right. Okay, but sometimes the way you look at it helps you kind of think about the problem. All right, so one of the points here is that there's going to be many different ways to parameterize the same object. In fact, there's always many different. Once you found one way to parameterize, you can always modify it. Just like when you parameterize a curve, you can always modify it by changing the speed, right? In a way of your parameterization. So here, same idea, right? I could parameterize this in two very different ways, right? Right here we have this root 2 over 2. But here, there's no root 2 over 2 or anything like that, right? But of course, you're still describing the same object. Okay. Let's see. So one thing, maybe a good exercise for you, maybe pause right now and figure out different angle cones. So what about cones of different angles? Right? Maybe what happens if you have a cone that's thinner, right? So maybe z equals 10 square root x squared plus y squared, right? How would you parameterize that? Okay. All right. Oh, by the way, I guess maybe one more of these examples. So we're doing a lot of these kind of parameterization examples because everything we do in integration on surfaces is going to be based on parameterization. So if you're not comfortable with parameterizing a surface, you're not going to be able to do any of the problems. All right. Okay. Let's revisit paraboloid. Right. So we had our paraboloid z equals x squared plus y squared. Right. We parameterized it with kind of the function idea, u comma v comma u squared plus v squared. But we can also do this with, for example, polar coordinates, right? Why would we want to? Well, because we know that x squared plus y squared in polar coordinates is simple. So this is just z equals r squared, right? And so we know we can describe our location on the paraboloid with just theta and, for example, r, right? So we could do an alternative parameterization, which is, again, based on r and theta, right? So x of r and theta, y of r and theta, z of r and theta, equal to r cos theta, r sine theta, right? And z is equal to r squared. Okay. All right. So this is, again, an alternate way to do a parameterization. And this one is even the difference between the two parameterizations that we've done is much more dramatic, right? Before we use this, right? So these two parameterizations are actually very, very different in a way. Okay. Actually, let me draw this picture to kind of emphasize this. So for the r theta parameterization, if you do a kind of r theta grid in the r theta plane, right? How would that grid transport to the paraboloid? It would transport, like we've kind of said this a few times at this point, it would transport kind of like that, right? So this grid becomes that grid. Okay, so in fact, this little rectangle would kind of become that curved rectangular-like object there. Okay, whereas here with the xy parameterization, x and y, if I did a grid here on the paraboloid, it would actually look like something like that. Okay, so it's actually very quite different. Okay, it would be slices. Actually, let me maybe make a more accurate picture. Yeah, more accurate. Oh, sorry. This should be U and V, of course. So it would be like, actually look like that. And like this. So the grid would look like something like that. All right. Because when you slice it, you're going to get paraboloids, parabolas. So you're kind of looking at these two parameterizations are approaching this paraboloid very differently. All right. Okay, and of course, in certain problems, you might want to use one parameterization. In other problems, you might want to use other parameterizations. Okay, so now that we know how to parameterize surfaces, hopefully. Oh, by the way, sorry, I guess I should say... No, we're okay, we're okay. All right, so next, we're going to integrate. So now that we can parameterize surfaces, I was saying, right, we have a surface here, we have a parameterization like this, maybe this region here corresponds to the part of the surface we're interested in, right? We want to now integrate on this surface. Like we said, maybe this is, we want to describe the temperature on this surface, right? So at every point there's a temperature, right? So we want to maybe find the average temperature, or maybe we want to just find kind of the total amount of heat energy on the surface. So we want to integrate that temperature function. How do we do that? We're going to port it to an integral on the UV plane, and we'll do the integral on the UV plane. All right. So let's actually do that procedure. So remember, so luckily for us, we kind of already know how to do this with small modification. So remember the extra credit problem from a few homeworks back, or a couple homeworks back maybe, where you were asked to think about a mapping from the plane to the plane, but one of them we thought of as U and V, the other we thought of as X and Y. And you were supposed to kind of figure out this guy under this mapping actually goes to something which is curvy and horrible, right? So that's too hard to work with. So instead, you kind of think about the linear approximation, in which case it goes to a parallelogram, right? And what happens is that parallelogram kind of tells us if we want to integrate, we would actually want to integrate in terms of X and Y, but it's too hard. So we, in practice, integrate on the U's and V's, where things are just a nice rectangle, right? But we have to compensation factor. What is the compensation factor? Well, in the extra credit problem, I think one of the last parts was to figure out the compensation factor, and that was the area of this parallelogram. All right. So if this was delta U and this was delta V, right, then you came up with a formula for this parallelogram in terms of delta U and delta V, right? That guy right there, it was the compensation factor. Okay. And you were supposed to do a particular example of that. I think it was the mapping where you had the polar coordinates, right? Where this using the U and V represented polar coordinates, and the X and Y was just a regular X and Y. And so what you should have gotten out here was the actual conversion from polar coordinates between the conversion from dx dy to dr d theta, right? And so what you should have gotten was a u right here. If you didn't, that might be a good idea to go back and take a look at that problem and just write it out. Make sure you get a u, right? Because that's literally where that's another perspective of where the r d theta comes from, right? So u and v are the r's and the theta for that problem. And so what you should have gotten was r dr d theta. Okay. So that's kind of so we figured out the r dr d theta by kind of carefully analyzing sectors of the circle. But this way of analyzation, or this, that's a weird analysis, is much more general, right? So the analysis you did in that extra credit problem works for any mapping, right? Wasn't restricted to just things, where you could analyze the sector of a circle. And so it allowed us to ultimately realize that when we convert dy dx's to dy du's in just the two variable integrals, right, we had this factor which was the Jacobian, right, which was the determinant of dx du dy du dx dv dy dv in the two variable case, right, and of course the three variable cases was bigger. Okay. So why do we care about that today? Well, integration for surface is literally the same idea. All right. Now we have a surface here. We have our mapping here. We have a rectangle there, right? It maps to something which is not a rectangle, something kind of ugly looking, curved looking here, right? We would like to integrate on this surface, meaning we want to kind of add up values on the surface, right? So we want to chop this surface up into kind of small pieces, add up the value at each piece and so on, right? But of course, too hard, so we want to do it in a two variable setting in the U and V plane. But a rectangle here is not a rectangle there, so we need a compensation factor, right? Now this guy here is too unpleasant to work with, so we instead look at the linear approximation, right? And in terms of integration, the linear approximation is good enough, right? Just like we saw, what we just talked about, the linear approximation is good enough in terms of integration. So we can look at the mapping under the linear approximation. So this is the actual mapping. So this is the linear approximation. I'm going to put that in quotes. We're not actually going to even write that down. So here it's mostly conceptual. The linear mapping, the rectangle is actually just going to go to a parallelogram. All right. And that makes the analysis easier. That tells us that the compensation factor is going to be the area of this parallelogram. All right. So our integral on the right-hand side just becomes a du dv integral times the compensation factor, which represents the area of a parallelogram. Okay. All right. So the question is, what is this area? All right. What is this compensation factor? And here I'm going to I'm not going to actually calculate it. You could literally calculate it because you can write down a linear approximation of the mapping. And so you could literally do this. It would just be following the same steps that we followed in that extra credit problem. And you could just derive the entire thing, right? Might be a good exercise if you're really interested in this. But let me describe it in a different way that maybe will help you for the future. So I've kind of talked about this before. The right way to look at derivatives, in one variable calculus, the derivative of a function is just another function, right? In multivariable calculus, f of x comma y, right? Or, in chapter, for example, 15, the derivative of a function should be thought of in a way as a vector, right? For a mapping from the UV plane to the XY plane, I've kind of said that in the past that the derivative should be thought of as a matrix, right? And for a mapping from UV plane, for a parameterization from the UV plane to the X, Y, and Z space, right? Derivative should be thought of as a matrix as well, all right? And what is it going to be? Well, what matrix is it going to be? What are the dimensions of that matrix? So one way to kind of understand this is you can think of vectors here, let's say at this corner. The horizontal vectors, right, are going to go to a vector here like that, right? So a two-variable vector goes to a three-variable vector, right? Because in order to describe a vector in x, y, and z, you need three coordinates. So here, this vertical vector, two coordinates to describe it, needs three coordinates once you push it to the other side from this, under this mapping, all right? So that means that this vector here, in order to describe what it goes to, you're going to have to describe it with a matrix which takes 2 entries and outputs 3 entries. All right. So 2 entries outputs 3 entries. Okay, so it's going to have to be a matrix like this. All right. Okay. Why do I care about how vectors move? Well, because vectors represent the vectors kind of represent, so think of it like this, right? So when you move along this vector, just like in that extra credit problem, you can parameterize this horizontal length, and then that will go to a length here, right? And so the derivative of that parameterization is going to be, or the speed of that parameterization is going to be the length of this vector here. So these vectors here, in a way, when you push it to this side, it represents the derivative of your mapping. All right. And so what happens is if you kind of work this out, for example, like doing the analogous problems from that extra credit problem, but in the three variable setting here, you're going to get dx, du, dy, du, dz, du, dx, dv, dy, dv, dz, dv, oops, yeah, dz, dv, as the kind of mapping that pushes a vector here to a vector there. All right, and this is the correct way. Anytime you have a mapping, there's an associated mapping of vectors from your domain to your range, right? And this would be that associated mapping. Okay, so this takes a two entry vector right there, uv vector, and gives you a 3 entry vector, right? XYZ vector. Okay, this guy is the derivative of the mapping. And I'm going to put that, of course, in quotes because that's not precise at all. But this is actually mathematically the correct way to think of the derivative of a mapping. All right. Now, why did I go through all this derivative of a mapping business? Well, this I've already kind of revealed it. This vector here represents that side of the parallelogram. And this vector here represents the other side of the parallelogram, right? So we want the area of the parallelogram. What is that? That's the cross product of these two vectors, all right? So area of parallelogram of infinitesimal parallelogram, right? In other words, when we take delta u and delta v goes to 0, that's one way to say this, is dx du. Let me write it kind of in our notation of our vector notation. dy du, dz du, cross dx dv, dy dv, dz dv. All right? And so our compensation factor is going to be exactly this, right? As we saw from that extra credit problem, right? And kind of as we saw from the change of coordinates section. Okay. Now this is unpleasant to write all these dx, du, and all that business, dx, dus, and dy, dus, and stuff. So we can simplify this notationally, right? This guy here, what is this? This is just, again, what we're doing is we're pushing kind of a path in the u direction to a path down here in xyz, right? And the other one is a path in the y direction, in the v direction to a path in x, y, and z, right? And so this guy here would, in a way, represent the derivative of that path of that parameterized curve, right? And this second guy is the derivative of the vertical parameterized curve. Literally, if you calculate it, that's what it literally is. Okay, so the notation we use for parameterized, when we talked about derivatives of parameterized curves, right? The derivative was tangent to the curve on the other side, and so we used the letter t. So here we're going to use the letter t. All right. So I'm going to call this t. So here's where notationally the book kind of departs from kind of standard procedure again. Our book likes to use little t of u for this guy. I'm going to put an arrow because it's a vector. And this is naturally a vector, right? This is not the situation where I hate, where we're representing things as vectors that shouldn't be. These should be vectors because this represents actually, like I just said, a velocity vector. So this is naturally a vector, okay? And this our book calls little t of v. All right. I think more traditionally, books would use maybe a capital T and a capital T here, sub u and sub v. Of course, mathematically, if you take more math, you use a completely different notation. But if you are looking at perhaps at different calculus books just for practice, it's very likely they'll use capital T's instead. In fact, I've never seen another book use lowercase t's like this. So just be aware of that. Okay, so our compensation factor now, if we write it in terms of this new notation, is little t sub u cross little t sub v, right? I should have put absolute values here, right? Because this is when you cross, you get a vector. We don't want our compensation factor. It should be an area, right? So it should be the length of that vector. Sorry about that. So it should be the length of this guy here. Okay. All right. So ultimately, all this stuff that I talked about leads us to this. When you want to integrate on a surface, so here's some notation. Surface integral, the notation we use is double integral because we're integrating on a two-dimensional thing. So two integrals, just like when we integrate dx, dy, we have two integral symbols. The name of the surface down here, usually we call that S for surface. The function we want to integrate, f, and then we use d. So before, when we integrate over a two-variable thing, we use dA to represent area. But now, because it's a surface, we write ds. Okay. So if we want to integrate a function over a surface, again, maybe temperature function, maybe f represents mass density, and so now you would be calculating the mass of your surface here, right? So how do you actually calculate this? So this is the symbolic object, right, that represents the area. In quotes, the area under the graph of f, right, or the integral of f. The actual calculation is going to be integral r f and then dA. So this is going to be in the parameterized. So this is in the UV plane. All right. And in practice, this is going to be double integral over the region that corresponds to your surface, right? And we've talked about that a little bit, right? So this is why you always need to know the region that corresponds to your surface, right? So for a sphere, for example, you only want theta between 0 and 2 pi. You only want phi between 0 and pi. Okay, f, and of course this f, you need to convert it to u and v, right? So you're going to have to do kind of some backwards conversion, right? Because usually your mapping is in terms of x is equal to something in terms of u. Oh, no, we're okay. Sorry. We're okay. X of uv, y of uv, z of uv, right? Just to emphasize, ultimately, this thing should be in terms of u's and v's because we're integrating with respect to u and v. All right. I guess I'm running out of space here. Let me move this guy. Okay. And then we have our compensation. So dA becomes our compensation here, tu cross tv, and then du dv. All right. Or d dv du, whichever is appropriate. Okay. All right. So again, in terms of analogies, this would be like when we did polar coordinates, this would be like our r dr d theta. All right, when we just did two variable integrals. Okay, that's it. So essentially, now you know how to integrate on a surface. I could just tell you, integrate this or that on a sphere. You do the parameterization, right, using perhaps the parameterization that was based on spherical coordinates. You convert your function, right, into phis and thetas, right? You calculate the appropriate t sub u cross t sub v. What is that? Well, you just look at upstairs, right? This is your t sub u. That's your t sub v. You can calculate each of those. And then d phi d theta. All right. So no problem. At this point, you should be able to use this guy to do an integral on any of the parameterized surfaces that that we discussed just now, right? Or any, of course, any other parameterized surface that you come up with, for example, in the homework and so on. So this is obviously running a little long here. So I'm not going to do a concrete example, but let me do a partial example, right? So let's say just kind of a very simple partial example, just to make sure everything is cool. So let's say our mapping was x of uv equals u squared v, y of uv was 2u plus 5v, and z of uv was sine of u times v, like that. All right. Then let's say our function was f of x, y, z equals x plus 2yz, right? So this f of x this f of x of uv, y of uv, z of uv, what is that? You just convert it to uv's, right? So x is u squared v, so u squared v. Y 2 plus 2 times y is 2u plus 5v, right? Z is v sine u. Okay, so this guy right here goes into that entry right there. All right. T sub u cross T sub v. So T sub u is equal to the vector. So we're differentiating each of the coordinates x, y, z with respect to u. All right. So 2uv, 2, and then v cos u. All right. T sub v, I should put arrows here, is equal to u squared, 5, and then sine u. Okay. And so now we just calculate T sub u cross T sub v. That's going to be equal to ijk, and this is just brutal calculation at this point. 2uv, 2v cos u, u squared, 5 sine u, and so that's going to be equal to I 2 sine u minus 5 v cos u minus j 2uv sine u minus u squared v cos u plus k 2 times 5, so 10uv minus 2u squared. All right. Our compensation factor is not a vector, it's a function, so we want the length of that. So that's going to be the length of this guy right here. All right. It's going to be somewhat horrible for this particular example. There's nothing you can do about that. All right. Okay. And so that you can see once we've taken the length, right, you're going to have a function in terms of u's and v's. And that function goes right there. That function goes right there. Okay. Now you're only interested in this surface in a particular part of the surface. You convert that to the limits of integration over here. Okay. All right. So that's as far as I'm going to go in terms of an example here. But you should be able to do any integral at this point, right? And all the concepts carry over that we talked about. If you want the area of a surface, right, that would just be ds. The function you'd integrate is just 1, right? And you integrate over the entire surface. Okay. So this is really nice because this means for the first time in a way you can natively calculate the area of a surface without having to kind of think of it as, for example, in the past, as the graph of this, and then you have to kind of work like that. Or maybe you couldn't do that in the past, actually. I think maybe in second semester calculus, perhaps you thought about areas of surfaces by, you calculated some areas of rotational surfaces only, right? But now you can calculate the area of any surface as long as you can parameterize it, okay? Center of mass of a surface, or let me say mass of a surface first. Right? So if you have a probability distribution, or a mass density x, y, z, right, which tells you how dense your object is at each point, right, your two-dimensional object is, then the mass would be rho ds. Okay. And so now center of mass, right, would be average x coordinate, right? And then of course you have to have the density, comma average y coordinate, density, average z coordinate, density. And if you're uniformly dense, of course, rho would just be a constant, and that would make your life a lot easier. And then of course divided by the area, or sorry, by the mass, total mass. Okay, so all the concepts carry over very, very straightforwardly. And at this point, you can talk about stuff like moments of inertia and stuff like that. But our class, we're not going to go further than that. Okay, so just a couple more things. So the first thing is, in terms of integration, there's a special case, graphs, right? What I mean by graphs is when we parameterize using of graph, right? So z equals f of x comma y, right? The parameterization, the convenient parameterization was x of uv equals u, y of uv equals v, z of uv equals f of uv. All right. So for this particular parameterization, this is a special case because this is a parameterization that we use a lot, because a lot of things that we work with come from graphs. All right. So you'll be working with this parameterization quite a bit in terms of the homeworks and stuff like that. So let's just write down for this particular case what that compensation factor is. All right. So for this case, let's see, T sub u is going to be dx du, which is just 1, dy du, which is 0, because we're taking derivative with respect to u, dz du, which is f sub u, right? The partial derivative of f with respect to u. T sub v is 0, 1, f sub v. Okay, so T sub u cross T sub v actually looks fairly simple. ijk 1, 0, fu, 0, 1, fv. So that's going to be I times minus f sub u minus j times f sub v plus k. Okay, so that's going to be written kind of a little cleaned up, minus f sub ui minus f sub vj plus k. All right. So the compensation. Oh, by the way, remember we looked at this when we talked about when we first talked about parameterizations, right? This represents if you move in the x direction and you push this up to the graph, right? It represents that arrow right there, right? The velocity. Okay, and same thing with the y's. All right, in any case, the length of this is square root the just the length of a vector, right? The first thing squared, f sub u squared, f sub v squared, and then 1 squared. Okay, so the special case of a graph, you have this this as your kind of compensation factor, the Jacobian. All right. Okay. So this is nice. Maybe you'll be doing enough of these problems that relate to the graphs that you'll just automatically remember this. But this is not something that you have to memorize, because as long as you know the compensation factor should be T sub u cross T sub v, you can reproduce this guy right here automatically anyway, right? So I would say this is something, don't sit down and try to memorize this. All right. Okay, in any case, now we can, for example, integrate the part of the paraboloid under z equals 4, right? Using the graph idea. So if the function we want to integrate is f sd ds, this would be, in this particular case, whatever the function is, the compensation factor would be, sorry, I should write down a formula, right? Paraboloid z equals x squared plus y squared, right? So here we would be, our parameterization was, again, x equals u, y equals v. I should be a little more precise here. uv, right? I always like to write this x of uv, y of uv, just as a reminder that x depends on u and v. We're thinking of x not as a variable in itself. We're thinking of it as depending on u and v. Because again, we're working with kind of x's and uv's. It's very easy to get confused as to what's going on, what's the independent variables. And with all the stuff going on in this class, it's, getting confused is really bad. So this kind of ensures I don't get confused. All right. All right. So f sub u is equal to 2u. F sub v is equal to 2v. Right. And so 2u squared plus 2v squared plus 1 du dv. That's it. What region are we integrating over? Because we're under z equals 4, right? This is we're integrating over a circle of radius 2. Okay. All right, and then the really important fact is, of course, this guy right here is just a two-variable integral in the plane that we already know how to do. All right. So let's do our final subtopic. This whole chapter is called vector calculus. So obviously, we want to work with vector fields. So let's do that. So let's say we have a vector field in the XYZ space, right? So we have a vector field here. Let's say we have a surface here as well. Maybe I should, let me redraw this. So I have space. I have a vector field, right? Which again, we just represent as a vector at every point. And I have a surface. All right. So I'm interested in how this vector field behaves relative to this surface. All right. So we've talked about this idea with how vector fields behave relative to curves, right, in the plane. For example, when we talked about flux, right, we had a vector field, for example, in terms of just x and y. Right. Let me use the same colors here. Right. And we talked about maybe if we had a curve like this. Yeah, let's say a curve like this, right? We talked about the interaction between this f and this vector field. So one thing we talked about was the flux, right? The flux integral would be how much stuff, if you think of this vector field as stuff flowing, right? Fluid flow, is how much stuff is flowing across this surface, right? In that case, we had to give the surface a direction, an orientation. So for example, we might have decided we want to orient this surface or orient this curve in that direction, right? And if we orient the curve, in that direction, then that would give us, that induces a normal direction, right? If we wanted to talk about the flux. And the way you calculate that was from the cross product. So you cross it with k, and you would get the induced normal. In this particular example, if the direction of motion was that one, if the orientation was that direction, the normal, so we called that t, the normal would be this direction. Okay, so the flux would measure how much stuff is moving across this surface in the direction of the normal. All right, in this particular picture, it looks like the flux would be negative. All right, okay, we also talked about the interaction where you can talk about the circulation integral, or not circulation, the work integral, right? Circulation usually we reserve for closed loops. We could talk about the flow integral, right? How much liquid is flowing along this surface, right? Or how much work is being done as we move along this, sorry, I said surface again. How much fluid is flowing along this curve as we move along this curve, or equivalently, how much work is being done as we move along this curve, right? If we think of the vector field as force. So that also involved an orientation, right? We had to give a direction. Okay, so naturally, kind of judging by those, when we talk about the interaction of a vector field with a surface, we're going to need to give an orientation for the surface, a direction, right? So we're not going to talk about flow or circulation or work along a surface because that doesn't really make sense. Okay, so flux is what we're going to be talking about today. All right, flux across a surface, and that makes sense because, well, it's just measuring how much fluid is flowing across the membrane, across this membrane, right? If you think of it as a physical object. And again, when we talk about the word across, you're going to have to talk about one side to the other side. And so you need to describe the sides of the surface. All right. And how do we describe that? We describe it with a normal direction. Okay. So the direction that the normal points, that's the direction in which, you know, we're measuring how much stuff is flowing across the surface in that direction. So it pretty much ports directly from the curve situation, right? But again, the difference is that we're not going to have this idea of flow along a surface. Okay, it's just going to be flux across a surface only. All right. Okay, because there isn't such thing as along, right? For a curve, there's such thing as along. I'm moving along this curve from here to here. So I can measure the vector field along the surface, right, as I travel. But for a surface, there's no such thing as along, right? There's no moving from one point to another. It's an entire two-dimensional object. But across, the word across does make perfect sense. Okay, so flux. All right. Okay, so that's what we're going to talk about. So S is oriented if we have a consistent normal direction defined on S. All right, I want to use the word consistent because, of course, the normal should be defined at every point. And if I say the normal should be here, should be pointing, let's say, upwards here, I don't want it to be downwards there. All right, it should be consistent. If it's, in a way, colloquially upwards here, it should be upwards everywhere else. Okay? All right, we're going to use the word upwards a lot. And remember, the word upwards means the vector itself should have positive k component. All right? Because when we say up, we mean generally up in terms of the z direction. And if we have a different concept of up, let's say we want up to be the x direction, we'll definitely say that out loud explicitly. All right, so S is oriented if we have a consistent n defined in S. Just a cool thing, not every surface can be oriented. If you take a Mobius band, so in other words, if you take a strip of paper and you connect it, well, first of all, let's say you connect it so that this connects with that. So let me say it like this. This point, you glue it together at the ends, where this point glues with that point, and that point glues with that point, right? Then what do you get? You get a kind of a cylinder, or part of a cylinder, a strip of a cylinder, right? However, if you take a strip like this, and you glue it the opposite way, this guy glues with that. And you can do this with a piece of paper right now. Just rip a piece of paper and do this. You glue this with this, or tape this with this, right? Then what you're going to end up is what's called a Mobius band. It's not that easy to draw. So it's going to be like there's kind of this twisting here, right? And this guy's not orientable. You can't orient this. So if I decide that this direction should be the normal here, if I travel this normal all the way around, if I just kind of smoothly push it all the way around, because there's of this connections are kind of opposite, it's gonna, by the time I come all the way back, it's gonna point in the opposite direction. So you can't make a consistent orientation here. All right. If you want to do this with a piece of paper, you can draw a person here, right, with a left hand and a right hand. You can draw a person, you can keep drawing this person, left hand, right hand, right hand, right? Or maybe we do left hand and right hand in different colors. Okay, and draw the same thing on the other side of the picture, all right? Or draw it see-through, okay? So what will happen is when you glue these together, at the very end, you'll have the first person will kind of be superimposed on the second person, right? And what's going to happen is their left hand and right hands aren't going to match. And so that's the same phenomenon as not having a normal. Okay, so we say S is oriented if we have a consistent N defined on S. It's not always possible. And what that means in practice, at least for our class, is that you can't integrate on a Mobius band. All right, or you can't. You can't do flux integrals on a Mobius band. Okay, super interesting. All right, in any case, if you do have an oriented surface, then we can talk about the flux. And what is the flux? The flux across oriented surface, S, is going to be, and hopefully you've guessed it, SF dot n ds. That's it. All right. So your vector field, your normal direction, you're doing a surface integral, which we know how to do, parameterize, blah, 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 right? And you're integrating on your surface, or at least a part of the surface you're interested in. Okay. So this is, of course, I should probably emphasize across oriented surface. Oriented tells me I have an n direction. All right. And again, if you have your n direction in the opposite, you decide to orient it the opposite way, you would have negative of the flux, because instead of flowing from one direction to the other, right, it's your flow is kind of in a way opposite. Okay, now let's actually compute this, because as with the two-dimensional case that we've done previously when we talked about flux, this integral actually simplifies quite a bit, luckily for us. So what is this? This is equal to F dot. Now, what is the normal? So this is why I mentioned the T sub u and the T sub v kind of representing kind of moving along the surface. So T sub u, right, we said was kind of moving along the surface like this. T sub v moves along the surface like that, right? So T sub u cross T sub v, the direction of it, not the length of it, I don't care about the length at the moment. The direction of it is, well, we have cross product. The direction of the cross product of two vectors is normal. All right. So T sub u cross T sub v is perpendicular, always perpendicular to our surface. All right. So if we parameterize our surface so that T sub u cross T sub v is consistent with our normal, then the normal would just be T sub u cross T sub v over the length of T sub u cross T sub v. All right. Now, if we parameterized our surface so that T sub u cross T sub v happen to be in the opposite direction of the orientation that we've chosen, we can still use the same parameterization, just pop out a minus sign in front of the integral, right? Because in that case you've used the wrong normal, you used the wrong direction for the normal, right? So everything is negative of what it should be. Okay. So ds. Okay. All right. So this is, let me emphasize, if T sub u cross T sub v is in same direction as chosen normal. Okay, so for example, let me give an example here. If, let's say, I'm talking about calculating the flux across the surface of a paraboloid, where the normal is chosen to be pointing upwards, all right? So the normal is pointing in the positive z direction, all right? Then, so that would be an orientation for my paraboloid, all right? The normal vector is always pointing upwards, positive, the x component is positive, okay? Then when I do my parameterization, I would check, let's say I would only need to check this at one point, in fact. I check at one point, using my parameterization, I would check at one point what this guy is, what direction this points in, all right? So in other words, I check its k component. If its k component is positive, then I'm all set. If its k component is negative, then I better pop out a minus sign, all right? Okay, now that's one way we often talk about orientation, using the word upwards or up or down. Another word that we frequently use is outwards or inwards, right? So for example, if we were integrating over a sphere, one common orientation, probably the most common, is to say we want to orient the sphere with the outward normal, right? Because a sphere, there's such thing as inside and outside, right? So I can say the outward normal, okay? So in that case, I would have to check if I, if I do a parameterization of the sphere, and I calculated TU and TV, and I calculated TU cross TV, how would I know if I got the outward one? Well, I would check that vector right there at one point, any point, doesn't matter, and I would see whether it points outwards away from the origin or whether it points inwards towards the origin. Okay. Perhaps the most convenient would be to check, maybe one of the axis points right there, and you could tell easily, right? Is it in the, let's say, the y direction? Is it in the j direction or not? All right. Don't do it at the z at the North Pole, because remember, if you do spherical coordinates, the z direction, the North Pole is a bad point. All right, because things are actually being mushed together there. Okay, so make sure you understand how to determine whether your normal corresponds correctly to your chosen parameterization. All right. Okay. So let me give one more example. So here's an alternate situation. Let's say I'm talking about this paraboloid. But let's say I'm interested in not just the paraboloid, but the paraboloid plus the cap. All right. So now this surface has an inside and outside. All right. So now it makes sense for me to talk about the outward pointing normal. So in that case, the normal up here on the cap would be upwards, right? So if you do a parameterization, it's easy to check, right? Is TU cross TV literally k direction positive or k direction negative? But notice outwards on the paraboloid would be pointing like that. All right. So it would actually be the opposite orientation than compared to the one that I talked about earlier, which was the upwards one, right? Because these guys actually point kind of downwards. They would have negative k component. So be very, very aware of actually which direction your normals should be pointing in, right? Because if you don't have the right direction, and you don't kind of have the correct corresponding direction with the TU cross TV, your answer is going to be negative of what they should be. All right. Okay, so again, in this particular situation, you would calculate TU cross TV for the paraboloid portion of your parameterization, and then you would check, is it pointing away from the origin or away from the z-axis, right? Or alternatively, if you recognize it's always pointing downwards, right? Check if it has a negative k coordinate. Every problem is going to be different in this situation, all right? So be very careful here. Okay, one thing for graphs is that if you have a graph, the word graph, of course, in terms of f of x and y, f of x comma y, the word upwards always makes sense, all right? So you can always say the upward pointing, you orient upwards with the upward pointing normal or the downward pointing normal, okay? So those words always make sense. But again, upward pointing, downward pointing does not make sense for the sphere, right? Because here it's upwards, there's downwards. Okay. And again, you only need to check at one point, because as long as things are consistent, one point works, right? 1 point per parameterization. So here you have two parameterizations, the paraboloid and the top separately. So you better, of course, check those separately. Okay. In any case, let's continue. So normally, you can, at this point, you can just integrate this, right? No problem, because this is just a dot product. So inside here, this is just a function. So at this point, you're just integrating. Let me rewrite it. It's getting a little messy. F dot T sub U cross T sub V, right, over the length of that. And of course, we're dividing by the length because we only care about the direction, right? So we don't want the kind of length of the of this vector to kind of spoil our actual computation. All right, so this guy in here is just a function. So at this point, I could just say we're done. You go and calculate this dot product and integrate it, right? But luckily for us, just like in the flux case and the circulation case from earlier on, this simplifies. So if we actually write out this integral, convert it to the du dv integral, right? Remember the compensation factor, the Jacobian factor, tu was exactly tu cross tv, length of that. So actually, this is tu cross tv. It actually looks like this. Over that. So these two guys actually cancel, just like in the cases, again, from a few sections ago. And so this becomes just this. So luckily for us, flux integrals oftentimes are a little simplified, because we hate this absolute value term because it involves square roots, right? Because the length involves square roots. So for flux integrals, this kind of square root term often always cancels away. And so oftentimes you'll end up with an integral that's maybe simpler than you perhaps would have thought. Okay. All right, again, do you have to memorize this formula? You don't have to memorize it. You just have to memorize this guy here, that's the flux. And then you can reproduce everything that I've said about this computation here yourself, right? In fact, if you just sat down and started doing the computations naively by calculating the integral up here, right, you would actually have to convert the ds to du dv, and you would have to pop this guy out, and you know that they would cancel. I mean, they would cancel naturally anyway, right? So you don't actually have to memorize this, but it's useful in that if you were completely naive and did this calculation straight out, and you calculated the length of the cross product, you will have wasted a little bit of time writing out square root of something squared plus something squared and all that, right? Not a huge deal. So it's not something that again you need to memorize. Okay, but hopefully, right, you'll be doing enough homework problems and examples that it naturally gets committed to memory. All right. Flux is super important, so you definitely want to make sure you understand the concept of flux as well as how to compute, right? So again, here's a surface. If my vector field looks kind of like this, right, then it looks like if I chosen my orientation to be this direction, then my flux is going to be positive. All right. So by the way, so you could use this to check your answers, right? Make sure when you do flux problems, look at whether you get a positive or negative answer, and then try to reason out if you kind of understand what the surface looks like. Try to reason out, and if the vector field is simple enough, try to reason out, whether it should have been positive or should have been negative. All right. Now, of course, you can't always do that. Sometimes the vector field is just too ugly to kind of comprehend. But if it's simple enough, you should be able to reason it out. All right. So, for example, if my vector field is, something like this, x, y, z, it's radial, right? So this guy's pointing outwards away from the origin. And I calculate a flux integral around a sphere of radius, whatever, 10. I know my answer, my flux integral, if I use the outward normal, I know my flux integral is going to be positive, right? Because things are flowing out of the sphere. Okay. All right, so what's next? So next, now that we can do these kind of integrals, the next section, we're going to talk about an extension of Green's theorem, the circulation version. So circulation version of Green's theorem was integral of the curl inside here relates to the integral on the boundary, right? Now we're going to talk about integral, so we're going to extend that to surfaces. So integral of the curl on the surface, right? Well, remember the curl is a vector, so we have to do a little bit of modification of the words I just said, curl on the surface. We're going to be doing curl dot the normal on the surface, so it's actually something legal, all right? It's going to be related to an integral along the boundary, all right? So we already know how to do boundary integrals, so that's all set. And today we understand how to integrate something on the surface. So what we talked about today will allow us to extend Green's theorem, and that extension will be called Stokes' theorem. And in the last section, we'll be doing what's called a divergence theorem, where we're integrating over, for example, the inside of a sphere, a ball. Usually we call it a solid ball, right? So the divergence theorem says if we integrate the divergence of a vector field on the inside of something, right, that's equivalent to the integral, a flux integral on the boundary, right? So what's going to happen with this divergence theorem is the integral of the inside of a ball, a dv integral, right, is equal to an integral just on the surface of a sphere, a ds integral, all right? So integral dv will be equal to an integral ds. Here's going to be a derivative, something prime. So of course this is all in quotes, nothing precise, right? And here there's no prime. And up here, same idea. With Stokes' theorem, we're going to have an integral on a surface on one side with a derivative involved. And that's going to be equal to an integral on its boundary, a curve with no integral involved. All right. So this surface is, of course, the boundary of this dv surface. Okay, so those will be the last two sections, and it relies super heavily on this section here, both of these theorems. So make sure you're very, very, very comfortable doing these integrals.